Alright, let's summarize the take-home message from our last video. Note, bonds, we can essentially put them in three classes. Purely covalent, polar covalent, and ionic. Recall, ionic means we have greater than 50% ionic character. These are standard metal, non-metal. So if you're wondering, is this an ionic or covalent compound? You go back to the rules we learned like the first week of class. If it's a metal and a non-metal, we're going to call it ionic, because we're almost guaranteed with a metal and a non-metal to have greater than 50% ionic character. Two non-metals, normally we consider it a covalent bond, but now we're going to really call them polar covalent bonds. Because unless the two atoms in the bond are the same atom, it's going to be a little bit of polarity. The only way to get two atoms having the exact same polarity is if they're the exact same atom. But if that is a case, we will call that a purely covalent bond. Note, a carbon-carbon bond, a bond that bonds two carbons together, is a purely covalent bond. And it doesn't matter if it's a double bond, single bond, triple bond, the carbon-carbon bond is purely covalent because both atoms at the end of the bond are carbons, has the same electronegativity value since it is the same atom. All right, so the molecule F2, two fluorines single bonded together, purely covalent bond because they're both fluorines. All right, so at this point when we're doing Lewis structures, we've really been doing it the long way about it, just so we can see where Lewis structures come from. Now we're going to write Lewis structures. We're going to just have a general rule so we can fairly quickly, and I kid you not, the more you do this, the quicker you're going to get. I'm going to give you a nice assignment with a whole bunch of Lewis structures. The more you do it, the more you practice it, the better you get at drawing Lewis structures. It is very important that you draw Lewis structures correctly. Okay, if you had to say in Gen Chem 1, what are the two most important topics? All topics are really important, but to me the two bread and butter, the most important topics are limiting reagent problems and Lewis structure problems. Those are the two most important things. All right, so let's look at our rules so we can fairly quickly and easily draw Lewis structures. First thing, draw the skeletal structure. Which atoms are bonded to which atoms? Often that will be given to you, and here's a little hint. Usually the least electronegative atom is in the center. There are some big time exceptions to this rule, but in general, the less electronegative atom is in the center. Note, you are usually going to find if you have more than one of the same atom, those will be the more electronegative atoms. So in general, if you have three of one type of atom and one of a different type of atom in your molecule, we'll go through examples, the different atom will be in the center, the same will be what we call terminal atoms. Also note, hydrogen and fluorine are terminal. They are always at the end. They are almost never central atoms. Okay, so once you have the skeletal structure, you know what atom is bonded to what. Then you count the total number of valence electrons. Do not mess up your count. You learn to count watching Sesame Street. You learn to count before preschool. Make sure you count electrons correctly. If you can't, if your electron count is wrong, your Lewis structure is wrong, and everything we do in the whole next chapter will be wrong without a good electron count. Double, triple count, and make sure you've got the correct number of valence electrons. All right. Things that'll mess you up though, if you have a polyatomic anion, so your whole thing has a negative charge, you need to add more electrons to it in terms of the number of negative charges. If you have NO3 minus nitrate ion, that has an extra electron to make it negatively charged. You have to add that extra electron in your electron count. Polyatomic cations, such as ammonium, you have to subtract an electron for every positive charge. Don't worry, we're going to go through these examples. As we go through the examples, you'll see, oh, these rules aren't so bad. All right, so after you have the skeletal structure, the total number of electrons, you start adding electrons to your molecules, starting by completing the octets of the terminal atoms and making sure you have one bond to the terminal atom from the center atom. And you keep adding electrons to terminal atoms until two things are going to happen. One, you've run out of electrons, or two, all your octets are filled on your terminal atoms. If you have extra electrons after the octets are filled on your terminal atoms, those extra electrons go on the central atom. What if after doing that you find out some of your atoms, specifically your central atom, does not have its octet? Well, then you can use some of the lone pairs on the terminal atoms to make a multiple bond, double or triple bond with the central atom. Okay, those are the basic rules. Let's go through a number of examples so we can see what's really going on here. All right, so the first one I've kind of started, NF3. Note, valence electrons. Nitrogen has 5 valence electrons. Fluorine has 7 valence electrons, but we have 3 fluorines. 3 fluorines, each with 7 valence electrons. 7 times 3 is 21 valence electrons for the fluorine, plus the 5 valence electrons from this nitrogen means a total of 26 electrons. Double check that, make sure that's right. 26 electrons. Note that fluorine is more electronegative than nitrogen, therefore we're pretty assured that fluorine is the terminal atom, nitrogen is a central. This tells us we have a nitrogen with 3 fluorines bonded to it. All right, so that's how we're going to draw it. A nitrogen with 3 fluorines around it. We've got our skeletal structure, we've got our 26 count for electrons. Now it's a matter of putting the electrons in. And the way we're going to do that, I like to do it this way. There's no necessarily right way, just make sure you get all your electrons in properly. I put the bonding pair first because I know I have to have a single bond, 1, 2. Then I complete the octet, 3, 4, 5, 6, 7, 8. I complete the octet around the terminal atom. So there's 8 electrons. Then I need 8 on this side, and I just keep counting. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So, note if you're a math wizard, you'd realize, oh, 8 and 8 and 8, 8 times 3 is 24 electrons have been put in so far. I just keep counting. I prefer Sesame Street. But note, I've put in 24 electrons, I've got to put in 26. I have extra electrons after all my octets are filled on the terminal atoms, so these 2 electrons go on the central atom. So now the question is, are we done? Well, we are done if every atom, including the central atom, has its octet. Well, we already know that the fluorines do. We counted to make sure they have the octet. Does nitrogen have its octet? 1, 2, 3, 4, 5, 6, 7, 8. Yes, nitrogen has its octet. All the atoms have their octet. Everything is fine. Yay, there's our molecule. There is the Lewis structure for NF3. All right. Let's do some more examples. Let's work on these 2 right here. NH4+. Well, first of all, what's the central atom? Well, normally the least electronegative atom is the central atom. However, note hydrogen has to be a terminal atom. You can't have hydrogen as a central atom. Hydrogen can only form 1 bond to another atom. Therefore, we know hydrogen has to be the terminal atoms. Nitrogen must be the central atom, so we're going to put nitrogen in the middle and the 4 hydrogens around it. Now we have to do the electron count. Okay, we recall nitrogen has 5 valence electrons. Nope, we get that from the periodic table. Hopefully you have a periodic table around and you can just count all the nitrogens. On the exam, yes, you will have a periodic table. So, 5 electrons for the nitrogen. Note, each hydrogen has 1 valence electron. There are 4 of them, so we have to have 4 valence electrons for the hydrogen, but this has a positive charge. It has a positive charge because it is missing an electron. Nitrogen provided 5, hydrogen provided 4, but one of those electrons got taken away, so we need to subtract 1 electron because of that positive charge. 5 plus 4 is 9. 9 minus 1 is 8. 8 electrons. Do not mess up that math. All right. So I have to put 8 electrons in there. Note, hydrogen, we don't put 8 electrons around a hydrogen. Hydrogen only wants 2 electrons around it. So, okay, 1, 2, that's done. 3, 4, 5, 6, 7, 8. There we go. There's our 8 valence electrons. Cool. When we end up with an ion, when we have an ion, it is proper to say, okay, this thing has positive charge. The whole ion carries that positive charge, so we tend to put it in brackets and put the plus outside like that to indicate NH4 plus ammonium has the positive charge. The whole ammonium ion altogether is positively charged. All right, our next example, HNO3. Okay, what's the skeletal structure going to be? Well, I've got oxygens are the most electronegative. They're probably going to be terminal. I've got 3 of them, which also leads me to believe oxygens are going to be terminal. So what's a central atom? Well, hydrogen cannot be a central atom. Therefore, nitrogen must be the central atom, and we must have the 3 oxygens around it. The question is, what do we do with that hydrogen? Does that hydrogen go here on the nitrogen? Or where else could it go? Something, you just have to stick it in your head, keep it in there. Wait, what is HNO3? You recall, if we were naming HNO3, that is nitric acid. Anytime you have these acids, like nitric acid, sulfuric acid, perchloric acid, we know, well, you do now, that the hydrogen is bonded to one of the oxygens. Okay, so one of these oxygens contains the hydrogen. How do you know that? Because I just told you that. That's how you know it. Anytime you have something like H2SO4, the 2 hydrogens of sulfuric acid are bonded to oxygens. All right, so now you know that. When you see these little structures, don't get confused. Number 1 mistake I see is, well, people, okay, nitrogen's a central atom, and so they'll put the 3 oxygens around it, and then they'll put the hydrogen off the nitrogen. No, 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 no. Nitric acid. If it's an acid, the hydrogen goes on one of the oxygens and not the nitrogen. Okay, there's my skeletal structure. Now we need to count electrons. Well, hydrogen has 1 valence electron. Plus 5 for the nitrogen, plus, well, oxygen has 6 valence electrons, but there's 3 of them. 6, what is 6 times 3? Do you know? I hope so. Is it 18? 18 plus 5 is 18, 19, 20, 21, 22, 23, 24. I got 24 valence electrons. Am I right? I gotta check. Okay, 1, 5, 6 times, 6 times 3 is 18, and that's 18 plus 6, and 18 plus 6, 24. Okay, I've done it twice. I think 24 is right. I hope so, because if you get that electron count wrong, oh my goodness. There will be questions on the next exam, the one question worth 10 points because of all the things you need to do, and it starts with a Lewis structure. You miscount the electrons, there's no way to get any credit. That was the first thing you had to do. Count the 24 electrons. You miscount, then everything after that's wrong. 0 out of 10 because you miscounted valence electrons. It's brutal, but that's the way it is. Okay, so make sure that electron count is right. 24 is right. Now we need to put them in. And I'm going to start with my central atom again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Note, I have to have a bond between this oxygen and that hydrogen, so I'm going to put 23, 24 there. Yeah, I've got to have a covalent bond. So this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has its octet. This hydrogen has its 2. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8, has its octet. This oxygen has its octet. I've put in all 24 electrons. If you counted 8 and 8 and 8, There's 24 electrons. Does nitrogen have its octet? No. Nitrogen does not have its octet. So what do we do if we do not have enough electrons for all to have octets? We're going to use a lone pair on one of these oxygens to form a bond with the nitrogen. Now the question is, which oxygen do we form a bond with the nitrogen with? Coming up in the next video, we are going to see that we do not use the oxygen that has the hydrogen on it. Why? You can't handle it yet. We'll worry about that next video. But what we're going to do is take 2 of these electrons from one of these oxygens and make a double bond there. So then we end up with, I'm going to redraw it. Note this oxygen still has its lone pairs. There's the nitrogen. This top oxygen has a double bond and 2 lone pairs on that oxygen now. Single bonded to this oxygen, single bonded to the hydrogen. And that is the Lewis structure for this molecule. All right. Whew. Good stuff. Let's do 2 more examples. We'll end this video with 2 more examples. Let's look at CO2, carbon dioxide. Alright, I think at this point you can safely sure that carbon is in the middle and the oxygens are on the outside. How many electrons total? Well, carbon has 4 valence electrons. Oxygen is 6 times 2. Well, I know that already. That's 12. 12 plus 4 is 16 electrons. Are we sure? Okay, oxygen, 6 times 12, 13, 14, 16. Okay, 16 electrons. Let's put them in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Note I've completed my octets on my terminal oxygens, and I've put in all 16 electrons, but does carbon have its octet? No, it does not. So, what do we do when the central atom carbon does not have its octet? First thing, let's take 2 electrons from this oxygen and move them up there. Ooh, will carbon have its octet at this point? Well, let's just do it the long way. In a week or 2 you'll be able to just see, oh, okay, I know what to do without doing this extra step, but let's draw it. Let's draw the double bond and the 2 lone pairs on that oxygen, and then the single bond and the 3 lone pairs on this oxygen. Does carbon have its octet? No, it still does not. So what do? You can see we've got 2 choices. We could take 2 electrons from this oxygen to make a triple bond, or we could take one of the lone pairs from this oxygen and make another double bond. What we are going to find out, and we will find that out when we discuss in the next video, when we discuss the next topic, formal charge. We are going to find out that it is much better to take a lone pair from the other oxygen and make 2 double bonds instead of a triple and a single bond. So now we've got the double bond on the left carbon, the double bond on the right carbon, and our right oxygens there, and there is our molecule. Carbon dioxide is a carbon with 2 double bonds to oxygen. Alright, our last example for this video, N2. Got a nitrogen, and another nitrogen. Note, if there's only 2 atoms, it can't have a central atom. How many electrons? Well, each nitrogen has 5 times 2. We know we've got 10 electrons. Well, how do we even start this? There are various methods to start this. I'm just going to say, hey, pick one as a central atom and then do like normal. So I'm just going to say, oh, let's pretend this nitrogen was central. They're both the same atom. We only have 2 atoms. There's no such thing as a central. But if we pretended this nitrogen was central, that means I have to fill my octet around this one. 1, 2, 3, 4, 5, 6, 7, 8. I've got 2 more electrons to put in. They go on the central atom, 9, 10. All right. Well, that doesn't make much sense there. Does this, well, this nitrogen has its octet. We counted them. This nitrogen does not. So what is our plan to give the other nitrogen its octet? Well, let's take these two electrons and make a double bond with them. Note when we do this, this nitrogen will have 1, 2, 3, 4, 5, 6 electrons. It still does not have its octet. So then let's take these two electrons and make a double bond with them. And when we do that, we find we have the left nitrogen with its lone pair, a triple bond to the right nitrogen with its lone pair. All right. So there we go. There's the Lewis structure for N2, a nitrogen-nitrogen triple bond. Question, how strong is a nitrogen-nitrogen triple bond? The answer, very strong. And this leads us to something kind of interesting. I'll make this short. 80% of the air we breathe is nitrogen gas, N2 gas. We breathe in this nitrogen gas, and what does our body do with the nitrogen gas we breathe in? It breathes it right back out again. Your body can't do anything with the nitrogen gas, with the nitrogens of the nitrogen gas you breathe in. Now your body needs nitrogen. Our proteins have nitrogens in them. Our DNA has nitrogens in them. Our body needs nitrogen atoms, but it cannot get them from the nitrogen in the air. Question, why can't your body get the nitrogen atoms that it needs for you to live from the nitrogen atoms in the N2 molecules in the air? Because a triple bond is strong. The nitrogen-nitrogen triple bond is a very strong bond. Your body doesn't have a way to break it down. Your body cannot break down a nitrogen-nitrogen triple bond. So N2 molecules go in you. We have no way to break them down to get the nitrogen atoms, so they go right back out. And therefore, any nitrogen that you need to get in from your food. Any nitrogen atoms in your proteins or your amino acids or your nucleic acids, your DNA, comes from your food, not from the 80% of the air that you breathe. All right, that's it for this video. We will next look at formal charge.